Okay. Hello, everybody. I'm Matteo, for those who don't know me, and my thesis is on the kinetic modeling of plasma thruster plumes. So let's start with some brief questions about my thesis. So let's start from what is my thesis? And well, I told you the title is Kinetic Modeling of Plasma Thruster Plumes. And the best way to explain this, I think, is to subdivide it into two parts. So let's start with the plasma thruster plumes. What's a plasma thruster plume? Well, here you have a complicated sketch with a lot of information, but the basics of it is that the plasma thruster plume is that part of plasma which is ejected by the thruster and which is collocated in front of the thruster exhaust. And it's composed by ions, which are the Swiss flags over here, electrons, which are neutral particles, and neutrals, which are the purple ones. Now, what is kinetic modeling? Well, the best way to describe kinetic modeling, I guess, is as opposed to fluid models. So in the case of fluid models, we use a variation of the Navier-Stokes equations, which ignore the specifics of the single particles that compose the plasma. So we do this by, for example, taking the average velocity of the fluid rather than the single velocity of each particle. However, if we want to maintain this detail, we can move to kinetic models, such as, well, the most common one is particle in cell, or PIC, which we will here talk about in the next talks. How does this work? Well, the idea is that we simulate the particles in the plasma with macroparticles, which we move around, integrating their equation of motion. Then at each time step, we compute the electric charge at all points of the domain by summing up the positive ion and the negative electrons. And this charge density enters the Poisson equation and gives us the electric potential and the electric fields. These can then be plugged back into the equations of motion, and this loop continues infinitely. Now, why is my thesis? Well, the most practical objectives are the one to characterize the interaction between the plume and the spacecraft, which can lead to erosion or electrostatic charging. And in some cases, the plume can also provide part of the thrust. So this is the case for magnetic nozzles. There are also some other more, let's say, specific applications like thrust vectoring or debris removal. And all of this would, well, my thesis would be pointless if all of this was well understood, but there are some important points. So one of them is the facility effects, which we mentioned this morning. So this is the challenge of extrapolating the measurements in a facility, in a non-ground facility, to the operation in space. Another point is that the physics of electrons, and in particular their thermodynamics, is quite complex. And here we go back to the need for a kinetic model for electrons. Now, I won't enter into detail about this because we will be here all day. And then also some more specific problems depending on the thruster, such as the detachment of the plasma from the magnetic field and the influence of collisional processes. Where is my thesis? That's easy. How is my thesis going? Well, we started with a lot of enthusiasm on the concept of a quasi-neutral peak, which would have been an advanced and new approach. But then we had some deadlines on the ESA project that we're working in, so we had to stop this. And for the Commodis project, we have been simulating both a grid ion thruster and a helicon plasma thruster. Then we also started to work on the magnetic arc for the Zarathustra project, and because this wasn't enough, we also started thinking about cathode simulations. This is the result. Now, this is too much stuff, so let's just concentrate on the grid ion thruster simulations. And this is the setup of the simulation. Now, here there's a lot of detail, but the main takeaway from here is how a grid ion thruster plume works. So a grid ion thruster emits ions and electrons separately. So ions enter into the domain with a large velocity and just proceed straight downstream, while electrons are emitted by the cathode, and then they enter into the plume and neutralize it. Another novelty in this simulation is that we are subdividing these two particles, so ions and electrons, into subclasses. So ions are divided into fast and slow ones. This is easy. The fast ones are the ones injected by the thruster. The slow ones are the ones produced in the plume, which have a much lower velocity. So they are produced in the plume by ionization, for example. Electrons the physics is a bit more complex, but we can divide them in trapped and free. The idea is that the potential profile inside of the plume is capable of trapping electrons inside it, in principle, for an infinite amount of time. So these will be the trapped ones. The free ones are the ones that can reach the edges of the simulation and leave. And okay, let's start from the general plasma response. So here there's, again, too much detail, but let's look at the two plots up on top here. So these are the fast ions that I was telling you, and these are the slow ones. And what we see here is that I was telling you the fast ions just enter the domain and leave axially without really expanding too much under the effect of the electric field, while these low ions are the ones which are produced inside the plume, and since they have a slower velocity and a smaller inertia, a smaller kinetic energy, their trajectory is inversed by the electric field, and these are the ones that then potentially can interact with the thruster or with the spacecraft. So if you are interested in spacecraft interaction, this is the population that we need to look at. The other important result from this simulation is the potential over here. As you see the values of this potential map, there's quite a small variation in potential. So let's say the range goes from 0 volts to 6 or 7 volts. This is a novelty with respect to the literature, because the simulations of this kind of thruster present potential ranges of 60 volts, 100 volts. And why is this? Well, the response is in that separation that I was mentioning about trapped and free electrons. So here on top you have the free ones. Here on the bottom you have the trapped ones and their properties. And if we just look at the densities, you can see that the trapped ones are much more numerous than the free ones. These are the ones that end up neutralizing the plume and lowering the potential. So because in our simulations we introduce inelastic collisions, this is the mechanism that produces these trapped electrons, which then go and lower the potential. And you can see this from here. Again, too much information, but let's just look at, this plot, which is the axial plot of the density of trapped electrons, so along the plume axis. And the green line is the trapped electron density without inelastic collisions. The other lines are all including inelastic collisions. So you can see here that the trapped electron density is an order of magnitude lower. And the result is that if we go to the potential map along the axis, which is this one, the green line reaches 60 volts, more or less 50, 60, while the other lines are around 5. So we see that if we exclude inelastic collisions, suddenly the electric potential rises a lot. And this is a novelty and, highlights how important the inclusion of inelastic collision is, which is something that up until now has been ignored. So I hope I'm on time. Let's just talk about the next steps. So with all this mess about all of these, working branches, we are planning to bring the magnetic arc simulations, which I have not talked about, to IEPC this year, as well as the ones of the grid ion thruster. Then we hope to turn these into articles. Then, we need to keep going on the helicon plasma thruster simulations and the comparison with Chalmers experiments. And I would really like to get back to the quasi-neutral peak. And honestly, then about the cathode, I have no idea. So these are the contributions. A bunch of conference participation, some pending publications, and the project contributions for Ecomodis. And that's it. Okay, so if you have any questions.